Okay, so I'm going to do the ring of charge problem. So here's a ring, and it's a total charge Q and a radius R, big R. And we want to know, our point P is out here along the center line here, okay? So our strategy, as always, is to pick a little DQ and see what it gives in terms of a DE. So there's our DQ. We're going to draw our R vector from DQ to point P, or actually, my bad, from P to point P to DQ is our actual little R vector. All right, it's our position vector. And we're going to say that that distance here, that point P is a distance x away. Okay, so I'm just following what I did in the slides. So that's the way you can follow along with this. So now that we've got that set up, what does this red DQ give us at point P in terms of an electric field? It gives us something pointing directly away, right? So now we look at our other DQs, like what's happening here. I'm going to pick another color. So what if I looked at that DQ? What DE would that give me? And I look along here, and it would do that. It would be directly away from that DQ. Okay, that is not perfect, but I think you know what I'm saying here. So hopefully you see that symmetry, right? So if I break those guys up, and then I'll go back to the red. And I break those guys up, right? Hopefully you will see that the actual, resultant, right, is, right, that the y components cancel and we actually get just the x components adding up, okay? So what's interesting here is if you look at DE and you're actually looking at that as a vector, we can write DE sub x and DE sub y, right? And let's go ahead and define a theta here. Okay, so there's a theta. So hopefully you can convince yourself, right, that DE theta, or sorry, DE sub x is DE times cosine theta, right? And DEY is DE times sine theta. And you might say, okay, like, what am I going to do with theta here? This is a triangle, right? This is R, this is X, this is capital R, okay? And it's just a 90-degree thing where, little r is x squared plus big R squared, right? That's just triangle stuff. Here's theta. Well, cosine theta is adjacent over hypotenuse, so it's x over r. Sine theta is r over r. Okay, so all I have to do is plug those in for cosine theta and sine theta. Okay, so back to this at hand. I write my DE as k dq over r squared, and when I integrate both sides, right, you're going to realize that r is going to be constant, so that'll be really awesome. But rather than just like straight up integrating, let's get ourselves in our component land. So the electric field at that point is going to be, we can call it E sub x, and it's the integral of all the dE sub x's. So that's k dq over r squared times cosine theta. okay? Now, let's keep going. Oh my goodness, k dq over r squared. So we said down here that cosine theta was just x over r, right? That's just cosine theta, cosine theta. So let's keep going. K dq over r cubed, and then what do we still have? X. Okay, seriously, hold on. I'm going to write this k, x, dq over, by the way, r was that, right? So r cubed is x squared plus capital R squared to the 3/2. So x is the distance away from the ring. R, capital R, is the radius of the ring. This whole entire beast is constant. Okay, so that's like awesome. So we get kx over x squared plus r squared to the 3/2 integral of dq. That one I can do. Integral of all the dq's is just the q total, which was given as q. So your final answer is this bad boy. Okay? Boom. Glorious. Pause. Okay, so all of that was slide 13 on the slide deck. This is going to go over slide 14. So we want to look at some limiting cases. So the first limiting case that I want to look at is very far away. So I have my little ring, and I want to look very far away. So what do you think that's going to look like? Hopefully, right, you realize it's going to look like a point charge. So let's prove that, okay? So how do we actually like mathematically describe this? Right? Sort of x is going to infinity, and r is going to 0, capital R. Okay? So when we see kxq over x squared plus r squared, okay, let's look down here. If r is going to 0, right, then that guy's going to go away. So we get kxq over x squared to the 3/2. X squared to the 3/2 is going to be x cubed. So look at that. There's your point charge. Nice. Okay. The next limiting case is where you're very close. And so that's where you have a very small x. Okay? So you could also say r is much, much bigger than x. All right? And that's going to look like this. It's going to go to kxq over r squared. So, I mean, a little bit, right? It's just if you're comparing x squared to r squared, there's sort of more robust ways of doing these approximations, but this gets the general gist. But what that shows you is that it goes as x, so it's like linear. So the actual sketch and you can sketch this on Desmos actually, or whatever program you want, is that it's going linearly, right? So it goes as x. And then over here at some point it's going to go as 1 over x squared. And then when you actually plot, right, this whole thing, it looks like that. So there's some interesting, points at which things happen. But what is important here is that the electric field at that center of the ring is 0. Hopefully you are convinced by that, right? And so that makes sense that the electric field should be 0 at x equals 0, and that works here, right, if x equals 0. And then it might not be obvious that it goes up linearly, and that's fine, but the limiting cases of E equals 0 at x equals 0, and then you can figure out that going as linearly, and then the looking like a point charge from very far away, those should be something that you should be able to figure out. Okay, I hope that helped.